Thank you. So before we get started, I would like to ask you, who here is already using Zio in production? Very good. Who here has at least tried out Zio or evaluated it or is thinking about using it? That's very good. I want to get this to all of you soon. Let's see. For today, we will try building a few applications with Zio and see what are the issues that we run into and where the shortcomings of the kind of Zio best practices are. And then I'll show you a small library called Zio Macros that was mentioned a few times throughout yesterday and today that aims to solve some of these pain points. So before we get started, I'd like to do my take on the Zio introduction because we didn't have enough so far. So you all are aware of I/O data types. So I/O or future, even though it's broken, or similar data types. They basically only expose two operations: pure, which you can use to lift the pure value into this effectful computation, and flat map, which you can use to take what is inside of this data structure, transform it, and also embed an effect into this data structure. In this case, it is the effect of asynchronity, so running an asynchronous process that may or may not succeed or fail. But it turns out this is not the only data structure that kind of shares the same structure. Another one that all of you know is either. It follows the same pattern. You have a function pure that allows you to lift a value into an either, and you have flat map that you can use to transform the value and embed another effect into this structure. And in this case, this is the effect of failure of typed errors, so to say. So you can say an either is a computation that may succeed with a B or fail with a trovable, for example. Another one that follows also the same pattern, but is slightly less well known, is a reader. Once again, same story, pure to lift a value, or flat map to embed an effect. And in this case, it is the effect of reading from the environment. So querying the context, pulling some configuration out, something like this. And the interesting part about Zio is that it kind of combines these three data structures. So in its three type parameters. R essentially represents your reader, or your reader T or Kleisli, depends on how you want to think about it. E represents your typed failure, and A is just your regular asynchronous effect. And kind of what makes Zio that powerful and that expressive is the combination of these three very common effects in one first-class data structure. In this talk, we are going to focus more on this R parameter. There is very much to say about the other parts of Zio, but here we really want to focus on the environment environment type parameter and how to work with it. So also, if you're not super familiar with Zio, we'll step through code quite quickly, but you should try to focus on this R parameter and what is happening with it, because this will kind of be the main focus of this talk. So how do we actually work with this type parameter in Zio? This is this module pattern that was mentioned already. And basically, the main idea is we create a trait which has one abstract member that has to be of type of some service that exposes functionality that we care about. This is console taken from Zio's codebase, which just exposes the capability of interacting with the console, so reading a line or printing a line. The main reason for having this this wrapper trait is just to prevent namespace collisions if we compose them, and I'll get to that in a second, but this is the main reason for having these. The cool thing about encoding them like this is that if you're combining two effects that have different requirements, so for example, sleeping, which requires clock, and printing to the console, which requires console, you'll get an effect which requires both clock and console. And this is represented using this intersection type or compound type, clock with console. And using this function provide, we can provide an implementation of this environment and absolve this effect of its dependencies and make it dependency free. And this is all that is to be said about Zio's R parameter. It is very simple and kind of straightforward to work with. So I mentioned that we are going to build some applications with Zio. So let's get started doing that without spending time on other stuff. The first application I would like to look into, or build together, is Zio Keeper. You might have heard about this in an earlier talk. The thing is, I have an open pull request open for a membership protocol implementation, the Hyperview protocol that was mentioned. And I'm going to step through a few details to that implementation and show you where some shortcomings of this module pattern lie. So the same as with console or other modules inside of Zio, we have a type env inside of Keeper, or inside of this part of Keeper. This is basically just a wrapper around a few data structures that live in STM. And the intention here is to use this to keep track of the current kind of knowledge of this membership layer. What nodes are active, what nodes are in the passive view, and some other stuff that is helpful. And this behaves just like any other module. Another one that is available is transport. This basically just allows us to send messages to other nodes or receive a stream of incoming messages and deal with them. And the typical function that is in this part of Keeper or in this part of the PR might look something like this. So we have some sort of join message that we are receiving, and we want to handle it, so to say. So we'll grab all of the nodes we know that are active from our active view and just send them a message that says, okay, somebody has requested to join us, and we'll send you a forward join message. And then we'll add the connection to our active view using add connection. And as in the previous example, everything infers beautifully here. We have this nice big compound type with all capabilities that are necessary. At some point, console will be replaced with logging once that is ready, but for now it's like this. So everything seems cool. But what happens at the very edge of this layer, or the very border of this layer, when we kind of want to create our public API that the users will interact with? So we might want to have something like this, a function that creates this membership layer, passing in a bunch of configuration for the protocol. Of course, this can be wrapped like in a nice configuration data type or whatever. But the idea is here, we want to expose these capabilities as dependencies to our callers, such that we have proper inversion of control, and they can decide what we should use or override our decisions on effect implementations. And this is true for transport, random, console, clock, and so on. But what about this env that we were using, which is just used really for its reader capabilities and to pass around the state inside of our implementation? We do not want to leak this one to our callers. So we somehow want to use it inside the implementation of this function, but not expose it. And we want to do this in a generic context because we have the schedules we want to pass in that control when certain subprotocols are being run. And let's try to minify this situation a little bit. This looks something like this. So we have a base environment type that we need to have a generic subtype of, and we have a type that uses some sort of local environment additional. And we want to get rid of this. And now you feel free to try, but this is impossible to write on Scala. And this makes us very, very sad. I need to have some cats in here because of the dog. There are too many dogs already. But here we're facing kind of we're kind of stuck. There is no good way to go here. We can either leak env to our callers, which kind of breaks this encapsulation we were aiming for, or we can make our signature non-polymorphic. But then our API becomes less expressive, and we're kind of limiting what kind of schedules we can accept, and it feels weird to do it like this. Let's get back to this a little bit later. The second application I want to look at is basically every Ruby application ever that uses Zio. You may have hit that issue or that roadblock yourself. So typically you will have some sort of repository. In this case, the user repository, because this is what you use for generic examples. So you have a function add user, delete user, get user. Nothing interesting is going on here. And it's easy to provide an in-memory implementation of this. And now you want to write and you test it and everything is happy. But now you want to create your proper production implementation of this. Now you're using Doobie to implement this because you will have some SQL database running. So to use this with Doobie, you need to create a transactor. And creating a transactor is an effect itself. Rather, you get a catch resource which you can convert into a managed. In this case, we additionally have a dependency on blocking because we want to run this on Zio's blocking thread pool. But either way, the same applies. You will have your Doobie or user repository inside of some sort of effect or inside of managed. But this doesn't seem too bad. This is exactly what we want. We want to have resource allocation inside of our nice functional effect, right? If we get to our main function, this actually turns out to be very painful when we try to wire our environment. Because now we kind of have to create our environment in stages. You have to begin by pulling out the default environment, then using this to create our user repository, and then create our final environment using the user repository. It does not seem that bad for this example, but the main issue here is that it does not scale for complex environments or complex dependency chains, simply because there's too much to keep track of, and at some point you're basically doing what this stage is doing, just in your head, and this is simply unreasonable. And now so we'll get to this back later as well. And now let's look at the last example. You may have heard of this little library. That's actually Zio itself, or rather part of Zio's codebase. Zio has a data type called schedule. Schedule essentially implements a state machine where an effect can be evaluated on each transition between states. And it can decide to either continue or to shut down. And the idea here is to just have periodic schedules or schedules with exponentially increasing delay or up to really sophisticated cron-like scheduling of effects. We're doing this by embedding the effects that the schedule should run, including sleeping, directly inside of the transition. This makes the schedule very expressive, but this runs into a few issues. One of these is a function called delayed or delayed M inside of schedules implementation, or part of schedules public API actually. The idea here is that we want to modify the sleeps that are executed by the schedule. So say I want to halve all sleeps that are executed by the schedule. And the way we would like to do this is to essentially proxy or wrap the existing clock and just halve whatever sleeps are being sent to it. This works nice. But the problem is, if we want to do this in a generic context. Problem is that it's easy to create to pull out the clock using just r.clock. And then wrapping it is also easy, just create some sort of proxy. But now we need to somehow inject the modified clock back into the original environment. And this is done using the function g here, which has to be provided. So essentially it lifts a function from clock to clock into a function of r to r. So essentially kind of like modify from a lens. And this is super painful, and you don't want this in your public API ever. This is not nice. But that's kind of what we're stuck with, because we don't have any way to modify this in a generic context. So let's briefly recap everything we have learned about this R parameter, its current encoding, and shortcomings. We essentially want that combinations of R, or dependencies, requirements of effects, are compositional and can be fully inferred. This works beautifully with the current encoding, and is nice. We want to be able to essentially always downcast an R into a bigger R. So we can use something that just uses a console, where we would be able to use something that uses a console and the clock. This also works perfectly just by literally downcasting and type inference. But we also want to be able to effectively provide members of the environment to the environment, and we want to be able to effectively replace members of the environment. Those are essentially the two aspects that made the few examples that we went through hard to write or uncomfortable to write. And this is currently not possible. So I was saying at the beginning of my talk that I will show you a solution or propose a solution to this problem. There are many different ways of tackling this issue, and I think we've already seen a few of them were mentioned, but the one I want to talk about is a library called Zio Macros. So you can pull this into your project with SPT, just specify this as a dependency. The library itself is completely dependency-free and compiles for JVM, JS, to 11, to 12, to 13, and soon .E, not currently. So what is there to say about this library? What does it do? What does it do for you? This. The entire library just basically boils down to this one function signature. Given an A and a B, we want to be able to create an A with B. And we want to have basically laws on this composition of A and B. Specifically, we want traits that are implemented by both A and B to always use the implementation of B. So we essentially can override generically and extend environments generically. And the way this is encoded in the library is quite simple. The way this is encoded in the environment is using a type class called mix. This just takes 2 parameters and exposes a function mix that does exactly what we just discussed. And the only sophisticated part of this library is a macro that automatically derives this. This is literally the entire definition of the type class copy-pasted from the repository. There is nothing else going on here. Derived mix is a bit magical, but it's portable to Dotty and is basically just a black box macro that derives this. So how would you use this in practice? So given this mixed type class, and we have a trait bar, we can now write a function with bar that, given some implicit evidence, is able to compose a generic A with bar. So we can now just create a new foo and extend it by an implementation of bar, and then just directly call bar on it. This works in pretty much all cases you want it to work. So A can be any non-final class, and B can be must be a trait, and then it will work. Without any kind of gotchas, it will work. So this does not seem like it buys as much. This seems kind of low level. And it is a low level, but this is the foundation that we have other combinators built upon into this library. The most useful one is a family of functions called enrich with. So we have enrich with M, and enrich with managed. They do a bit of a manipulation of types, let's put it like this, in order to get good type inference, but they're not doing anything magical at all. So the idea here and the implementation of this is that they are wrapping some existing effect. So this is enrich with M. This just wraps a Zio of REB, and given a Zio that can provide all the dependencies of your original effect, it will chain the first effect to the wrapped effect, and then compose the environment or the outputs of both of these together using mix. And you use it just like this. So you can use it for pure functions, you can use it for effects, like you can use it for resources. All of these don't require you to specify any other type parameters other than the trait that you provide implementation for. And it also works for effects that require themselves dependencies in exactly the same way. Furthermore, we provide a little bit of implicit syntax on top of Zio. You can elect to use it or not use it. Everything it does, it allows you to call this enrich functions essentially in a chain instead of nesting function application. This just leads to slightly more readable code, but you can elect not to use it if you don't like implicit syntax. But given these few definitions, we can now start writing something like this. If you look into random with clock or collect with blocking, console with blocking, the idea is now we can just create a random instance and enrich it using a clock instance, and we get a random with clock. And the same works if we have dependencies on our effect that constructs this environment. for the enriched blocking with depth example. And if we now revisit writing our main using this machinery, it will look something like this. So we create our original environment, then enrich it with an SLF4J logger, then enrich it with a Doobie-to-do repository, and some default tracing, and then we pipe this all into our actual app. And I think this is as concise as construction logic as you can get. And everything is fully type checked. There is nothing magical going on at this layer. This is all just basic types and basic functions. Now, we can build more sophisticated stuff on top of this. Specifically, we can do some ghetto version of object-oriented optics with it. This is done using a function called patch inside the library. Basically, just using this implicit evidence, we can lift the function b to b into a function a with b to a with b. This is what we needed earlier, and this, I think, can be useful in a lot of interesting contexts. So you can use it to replace implementations. You can do whatever you want to do. Current kind of examples and stuff built on this is quite minimal, but I think it's a very interesting foundation to build more expressive stuff on top. And the last interesting part is local elimination. I guess this slide sums it up completely. This is just a more powerful version of provide some from Zeo's original API, and allows you to eliminate parts of the environment without much pain. Now, you have heard about this application called Polynode, and this was already mentioned, but they essentially define a type class enrich, which is surprisingly similar with mixed. What is cool is that we came up with this completely independently. So Polynode was, I think, not aware of us, and we were not aware of Polynode up until the point where this was sufficiently developed. But it's very interesting that we completely independently arrived at the same solution, basically. And I think this speaks a lot about how kind of fundamental this is. And the last thing I want to discuss is this magic? So is this a magical library? There, as usual with such questions, you consult the most important authority, Twitter, and dig out a blog post by John Digos. Magic is a feature with non-compositional semantics. It succeeds in making the common case easy, at the case of making the uncommon cases surprising, impossible, or ridiculously complex. Given this definition of magic, I would argue that this library, even though it's heavily based on macros and does things that are normally impossible in Scala, is not actually magic, because it offers very compositional semantics, and given just this one primitive mix, you can build very interesting stuff on top of it. And I'm actually looking forward to seeing what people can come up with basically on top of this. I mean, we've got basically lenses. Now we can try to do more sophisticated optics on top of this, however they may look like in object-oriented context. So thank you.